Understanding permissions in Linux. At a basic level, permissions in Linux are a relationship between users, groups, and files and directories. Users can belong to multiple groups, and groups can have multiple users in them. Every file and directory defines its permissions in terms of a user, a group, and others, which means all other users. User accounts are configured in the /etc/password file. User password hashes are stored in the /etc/shadow file. Users are identified by an integer user ID, also known as a UID. The root user account is a special type of account in Linux. It has a UID of 0, and the system grants this user, or more accurately grants this UID, access to every file. Groups are configured in the /etc/group file. Users have a primary group and can have multiple secondary or supplementary groups. By default, a user's primary group has the same name as their user account. All files and directories have a single owner and a group. Permissions are defined in terms of read, write, and execute operations. There are 3 sets of permissions, one for the owner, one for the group, and one for all other users, which can also be referred to as world. Only the owner can change permissions of the file or directory. File permissions are self-explanatory. When the read permission is set, the file contents can be read. When the write permission is set, the file contents can be modified. When the execute permission is set, the file can be executed, i.e. it can be run as some kind of process. Directory permissions are slightly more complicated. When the execute permission is set, the directory can be entered. Without this permission, neither the read nor the write permissions will work. When the read permission is set, the directory contents can be listed. When the write permission is set, files and subdirectories can be created in the directory. There are 2 special permissions which we will cover in this course. The first is the setUID or SUID bit. When this is set, files will get executed with the privileges of the file owner. The second is the setGID or SGID bit. When this is set on a file, the file will get executed with the privileges of the file group. When this is set on a directory, files created within that directory will inherit the group of the directory itself. The ls command can be used to view permissions. The first 10 characters indicate the permissions set on the file or directory. The first character simply indicates the type, e.g. a dash for a file or a D for a directory. In the example above, the first character is a dash, meaning that /bin/date is a file. The remaining 9 characters represent the 3 sets of permissions: owner, group, and others. Each set contains 3 characters indicating the read, R, write, W, and execute, X, permissions. SUID and SGID permissions are represented by an S in the execute position. So if we go back to the output of this command, the file is owned by root and is in the root group. The root user can read, write, and execute the file. Members of the root group can read and execute the file, but they cannot write to it. And finally, everyone else on the system can read and execute the file, but cannot write to it. I previously stated that users are identified by a user ID. In fact, each user has 3 user IDs in Linux: real, effective, and saved. A user's real ID is who they actually are, the ID defined in /etc/password. Ironically, the real ID is actually used less often to check a user's identity. A user's effective ID is normally equal to their real ID. However, when executing a process as another user, the effective ID is set to that user's real ID. The effective ID is used in most access control decisions to verify a user, and commands such as whoami use the effective ID. Finally, the saved ID is used to ensure that SUID processes can temporarily switch a user's effective ID back to their real ID and back again, without losing track of the original effective ID. There are a few commands we can use to print user IDs. Here we see the ID command, which prints real IDs of the user and the effective IDs if they are different. In this case, the user's real ID is 1000, and their real GID is also 1000. However, their effective ID is 0, and their effective GID is also 0. The second example will print the real, effective, saved, and file system IDs of the current process, which in this case is our shell. We will not cover the file system ID in this course, but it is usually the same as the effective ID. As with the ID command, we can see that our users' real IDs are both 1000, and their effective and saved IDs are both 0.